Lithosphere. Lithosphere is talking about the mountain, the rock. And in the mountain and the rock, what is the most common mineral on the mountain and the rock? Of course, the mountain and the rock itself, the rock, silicon dioxide, silicon and oxygen. Then what's come next? Aluminium, 8%. Next, iron, 5%. Remaining, sodium, potassium, calcium, magnesium. This 4 is the one that we come across many times. And then the rest is called the all other element. What's all other element? All the remaining metal elements on the periodic table. Gold, silver, copper, mercury, everything in this fine little line. And now let's look onto our human discovery onto this metal, this mineral. What is our earliest time? Of course, Stone Age, we're using stone. And then what is the next metal that we use? We use copper. Where's copper? Copper is on this fine element, this tiny weeny little bit of percentage of element, this tiny percentage of element. So is copper plentiful on earth? Of course not. It is quite not as plentiful. And then what's next? The next will be Bronze Age, which is the copper alloy. And then what's next? Then you come to Iron Age. That is about 3,500 years after, because of the technology until that age. And Iron Age, after that, until current, aluminium. So you find that our human discovery, it sounds a bit upside down. And people will think, look, aluminium is the most plentiful. Should we discover aluminium first, then second iron, and copper should be the last? But we discovered the wrong way round. How come? This is related to our activities of the metal. And now I list onto the most reactive metal on the top, the least reactive metal at the bottom, and hope that students still remember the activity series on our last lesson. And how does it correspond to our discovery of and the use of metal? Now let's see. I highlight the copper, iron, and aluminium as a typical example. Copper have the lower activity series, and they are easier to extract from the ore. So 7,000 years ago, mankind can extract copper from mineral called malachite because they are easier to extract. Next is iron. Iron have a higher activity series than copper, and they are harder to extract. So 3,500 years ago, mankind find a way to have that higher temperature to extract iron from the mineral hematite, because it requires higher temperature to produce. Aluminium is a much higher activity series, so very difficult to extract. Until the last century, 19th century, mankind can extract aluminium from the bauxite mine, and that is called the electrolytic reduction, using electricity as well as heat to extract aluminium. So student, what I want to emphasize on this list is of human discovery of mineral is not based on the plentifulness of that mineral itself. It's not based on the plentifulness of that mineral itself, but rather is based on the activity series, which is the easier to extract can discover first, and the hard to extract discover the last. And so we're going to talk more about this activity series related to the extraction of metal. Ores. What is ores? What is mineral? Let's define. An ore is a rock. It contains mixture of mineral, a mixture of mineral. So when you process this mineral, you can extract out the metal. So ores must have enough percentage of mineral to call it an ore. So if the percentage, the content of metal too low, we don't call it an ore. So you must have to have a sufficient percentage of mineral in it, and which is profitable to extract, and we call it an ore. Australia have two important ore, bauxite and the iron ore. Bauxite, aluminium oxide mixture. Iron ore, the mixture of hematite. And the next, mineral. What is mineral? Mineral is a compound with metal, a compound with metals. And these compound with metal are at a fixed composition, fixed chemical composition that naturally occur on Earth. And what is this mixture composition? I'll give you an example. Iron mineral, hematite, Fe2O3, magnetite, Fe3O4. Look at this Fe3O4. Can it be Fe3O5 or Fe3O6 or Fe3O7? No. They are restricted. They are at a fixed composition. They will be always magnetite, Fe3O4, hematite, Fe2O3. They are at a fixed composition. What makes them to have this fixed composition? And I hope students still remember a chart. Electron dot diagram. This ionic compound, remember, one magnesium needs two chloride to form magnesium chloride, MgCl2. One magnesium needs one oxygen, form magnesium oxide. So can it be MgO2, MgO3 or MgO4? No, because it's guided by this electron dot diagram rule, and so they are in a fixed chemical composition. So remember, what is mineral? A compound of metal at a fixed chemical composition. Now I'm going to go further about mineral. Mineral usually contain oxide, sulfide, carbonate, sulfate, silicate. Look at mineral. Mineral is a metal, positive metal, and a negative non-metal. A positive metal and a negative non-metal oxide, non-metal sulfide, non-metal carbonate, non-metal sulfate, non-metal silicate. And I hope students still remember this, the valency. Okay, and the charge. Okay, what sort of bonding are they? Are they covalent or ionic? They are a metal binding a non-metal. So this is an ionic compound. This is an ionic bond. So how plentiful are these minerals at ionic bond? Let's see. The most plentiful is the metal oxide. And I highlight on the table. You see, they all contain with aluminum oxide, iron oxide. So this is the common. The next one, magnesium metal with sulfide, another common mineral. The next two, metal carbonate and the metal sulfate, which is less. Okay, hope students still remember this oxide, sulfide, carbonate, sulfate, and the valency. Now let's go further. So on this extraction process, you see the metal of this activity series. It does affecting how they bind together. So on the top activity series, they always bind very tightly. They are always bind very tightly. And when you go on the lower of the group, they will frequently bind like tightly. You can say not as tight. But when you go on to the lower group, that you can find it in a uncombined form. So, and even if they combine, they quite easily extract out. So, on the top activity series, they always in a combined form. As in here, this is the hematite. It contains iron in it. And here it contains copper in it. All these they are in a tight combined form. They are in a tight combined form. So you very, very hard to extract them out. So, and on the lower group, they will be easier to extract. And when you're on the bottom group, you start to see they in a uncombined form. That's why you will find some naturally occur of the pure silver nugget as uncombined form and a pure gold nugget as being uncombined form. So, this activity series have important implication to show you how well would they be combined or uncombined. And this combined or uncombined form will directly affect our extraction process. As you go on to the series that we just been mentioned, you see on the top one, aluminium, they very hard to extract. Why? Because they are in a tight combined form. Iron, they are also in a high combined form. That's why they are hard to extract. And copper is on the lower combined form, and they are easier to extract. And how about gold, mercury, or silver? They are even on the lower on the table, so they are in a even more uncombined form that easier to extract out.